Hey y'all, it's Ms. Blasky. Today we're going to talk about all of the different states of matter and some of the vocabulary that's going to go along with this and how all of that relates back to this idea about intermolecular forces, IMFs. So first up, just a quick reminder of the difference between solids, liquids, and gases. Solids are much more structured. They have a lot less motion going on. They still are vibrating a little bit, but not a whole lot of translational motion, meaning they're not moving across a distance. Liquid molecules in, so like for example, this picture is for water. When we're talking about liquids, those molecules are moving a little bit more. They're able to have some translational motion where they're moving from one part of the container to another. So that allows for some more motion and some more opportunities for the breaking and forming of intermolecular forces. In gases, those intermolecular forces have pretty much broken completely, and those particles have full range of motion all throughout their container. So a couple of things that they talk about at this first paragraph talks about boiling point, which we've talked about already. A boiling point is higher when the intermolecular forces are stronger, because those molecules are being held more tightly together. It's going to require more energy to break them apart, to move from that liquid phase into the gas phase. Something that we haven't talked about yet is vapor pressure. So I'm going to show you something real quick about how vapor pressure works and what's going along with that. So here is a better image of talking about vapor pressure. So vapor pressure is different from boiling a liquid. Any liquid that is sitting out at any temperature has a very small number of particles of that liquid that have enough energy to be able to break those intermolecular forces and escape into the air above the liquid. Now, if you have a closed container, those particles are going to be trapped inside of the container. Those particles are able to move around. They're able to have enough energy to break those intermolecular forces and exist in the gaseous state. So because they are a gas, they exert pressure, and we call that vapor pressure. That vapor pressure will increase as we increase our temperature. It will also, as the temperature increases and increases and increases, we get closer and closer to boiling when we are putting in enough energy to actually get all of those intermolecular forces to break apart from that liquid and form gases. So this is why boiling and evaporation are different. So this process of these particles having enough energy to break their intermolecular forces on their own, that is what evaporation happens. We don't, if you leave a glass out on the table outside on a summer day, it doesn't start boiling. Just some of those particles get enough energy to break away from the liquid phase, form a gas. And if it's not a closed container, those particles are going to be able to escape out into the rest of the air. So vapor pressure is one of the things that we can talk about when we talk about intermolecular forces. If we have stronger intermolecular forces, that vapor pressure is going to be smaller because less of those particles are going to be able to break those strong intermolecular forces to form a gas. Specifically talk about solids first. Here's where we get into a little bit of the vocabulary. Solids can be either crystalline, however you want to say it, or amorphous. Crystalline structures are much more rigid. They have very specific shapes to them. This is an example of crystalline quartz. You can see that those hexagon shapes are in there. Quartz glass, though, we would consider an amorphous solid. Those particles are still connected to each other. They're still bonded. There are still intermolecular forces going on, but they are not even. They are not as structured, and so it's a little lumpier. The different shapes will have some differences in their properties. Crystalline structures are visibly different looking. They're usually very, they can have sharp sides or flat sides. They're usually a little bit shinier. Amorphous solids can melt a little bit easier. They can be a little lumpier. They can be smoother instead of having sharp edges. And so if you think about the difference between quartz, like the fancy quartz rocks that you find inside of geodes versus glass, you can sort of think about the difference between those shapes and how you can see that out in the world. Liquids are a little bit different. Liquids, we're going to talk a lot more about liquids in Unit 4, but we do need to know a little bit of things about liquids right now compared to solids and gases. The arrangement of the particles in a liquid still are controlled by intermolecular forces, but they have a lot more movement. They're colliding, the molecules are colliding with each other all the time, and so those intermolecular forces are breaking and forming a lot more quickly than they are in solids. Some special things that liquids have because of their intermolecular forces, surface tension. So that's what this picture is showing here. When we have surface tension, we have a very specific unidirectional intermolecular force on the surface of that liquid, while the intermolecular forces underneath that surface are able to form in multiple directions. So this unidirectional forces right on the surface sort of tightens that up and forms what we call surface tension. You see surface tension all the time, especially with water. Water has very high surface tension because it has very strong hydrogen bonding for its intermolecular forces. That's what lets water bubble up. If you've ever done the experiment where you put drops of water onto a penny, that's why the surface tension happens there. That's also why pond skater bugs can walk on top of water, because there's enough surface tension for them to hold up on. Capillary action is another property of liquids that doesn't happen for either solids or gases. It's where a liquid spontaneously rises in a narrow tube. You might see this with a drink in a straw. This is also how liquid gets up into plants and trees through their vascular system. So in this case, we're sort of getting the reverse of a bubble of water in terms of surface tension. We have adhesive forces between the molecules of the liquid and the sides of the container, and that actually becomes a stronger intermolecular force than the forces between the molecules themselves. And so the molecules of the liquid sort of creep up the side because they have a strong intermolecular force going on there. The narrower the tube, the higher up that tube the liquid can creep. Some substances actually have inverse capillary action. So water has what we normally think of as the meniscus curve. Mercury actually curves the opposite direction. It's convex, so it curves up because it has more attraction for itself than it does for the glass. Viscosity is also a property of liquids. It is a resistance to flow. So when you think of something thick like molasses or maple syrup or grease or something like that, it has a high viscosity. Molecules that have strong intermolecular forces have higher viscosity. So this example that we've got here, glycerol, has these 3 hydroxide groups, or these 3 OH groups, which each one of those is able to do some hydrogen bonding. So that's 3 locations available for hydrogen bonding for every 1 molecule. That's going to create a lot of really strong intermolecular forces between glycerol molecules to help increase that viscosity. Gases, we're going to talk a lot more about gases in the next couple sections. They're going to get their whole own section. But basically, we assume that intermolecular forces are not acting on gas particles. They are to a very small extent, but we can make a pretty decent assumption that that tiny bit of intermolecular forces happening between those molecules is not influencing their overall properties too much. So we can assume that they're moving fast enough and that they're far enough apart from each other to not have any intermolecular forces occurring. So now another little bit of important information specifically about different types of substances. We talked about ionic compounds last chapter, and we talked about how the positive and negative charges of the ions cause an attraction. That's a Coulombic attraction that holds the positive and negative ions together. So if we have larger charges of those ions, they're going to be held more tightly together. Notice that here in this magnesium oxide, the internuclear distance or the bond length of that is 212 picometers versus sodium fluoride, which has a +1 -1. That's a smaller amount of charge. And so it has a larger bond length or internuclear distance. We also talked about lattice energy. Lattice energy is going to come back while we're talking specifically about ionic structures. Because ionic structures are still, they're not intermolecular, but they are interparticle. They are much stronger than any of the other intermolecular forces we're talking about. So if we have to rank them, ionic forces is always going to be the strongest. But again, that structure of how those ionic substances are built can help us explain what happens. So ionic substances have low vapor pressure, meaning that's such a strong force that very few of those particles are going to escape into the gas phase. High melting point and high boiling point, meaning that those molecules are going to be held together tightly. They tend to be brittle, which means that if you whack them hard enough, they're going to crack instead of forming into new shapes. And this image sort of shows that, because if we hit those ions, we are pretty likely to be able to shift those structures, those crystal structures that they have, and get positive ions and negative ions to be across from each other. Those are going to repel each other, and so those two sections of that substance are going to push each other apart, and so that's when we see things crack. We also talked about ion dipole forces, and so that's another remembrance again about why we can get things that are ionic to dissolve in water. Because those water particles are polar, the positive sides of the water molecules are going to be attracted to the negative ions. The more negative ends of the water molecules are going to be attracted to the positive ions, and that is going to help that substance dissolve. In covalent solids, we have two main types of covalent solids. The first one is a covalent network solid. This is something that you just need to remember. You need to memorize what the examples of these are, because there's always at least one question on the AP exam about them. In a covalent network solid, we actually have covalent bonds between molecules or atoms. So one of the most common examples of this is diamond and or graphite, which is only made up of carbon atoms, but it is a structure of bonds between those carbon atoms that is repeating like a solid. So for example, this is what diamond would look like. Each one of these is a carbon atom. Carbon can form 4 bonds. And so each carbon is bonded 4 times to other carbon atoms. And it makes this very strong, very sturdy structure based on that tetrahedral shape, which is why diamond is such a hard and sturdy substance, because of that structure. Graphite, on the other hand, is still made of bonds between carbons, but instead of tetrahedral bonds, they make these 6-sided rings, these hexagonal rings, and then those rings form sheets. And so I think we've talked about this previously, about how graphite is the what's in your pencil lead. So when you're writing with a pencil on a piece of paper, you're actually sliding these layers across each other and rubbing those layers off onto your paper. 2 other examples of network covalent solids are silicon dioxide and silicon carbide. Silicon dioxide is one of the ingredients, one of the substances that's in glass. And so even though we have silicon dioxide molecules, they actually make this repeating pattern of covalent bonds, again, making that nice structure that lets us do things that we need to do with silicon dioxide. This helps it make it clear, this helps make it hard, this helps makes it brittle. And silicon carbide also does the same thing. It bonds slightly different structure, but is working the same ways. These are really the 4 examples of network covalent solids that you need to know, and you just need to know that they exist. Molecular solids are any other what we consider to be covalent molecules that are forming solids. So this would be water forming ice, or carbon dioxide forming dry ice, or any other molecular substance that is in its solid form. So this is where we have the intermolecular forces at their strongest for that substance holding those particles together, but not forming new covalent bonds between those molecules. Metals are totally different. They behave totally different than anything else. They have their positive ions, their nuclei, arranged in a pattern where their valence electrons then become loose and are able to move around in multiple directions. They call them delocalized around those positively charged ions. The electron sea is what that sometimes is called, SEA, like the ocean, is what allows metals to be able to conduct electricity so well. When we start mixing metals together, metals do not actually create bonds with each other. They just change how these positive ions are alternated. And we call these alloys. So there is not a covalent bond, there is not an ionic bond between them. They just alternate their ions. So two different types of alloys. A interstitial alloy is when we have metals that have very different radii or atomic radii. And those smaller atoms fill in some of the spaces between the larger atoms. And again, their valence electrons are just going to join the larger atoms' valence electrons in that electron sea surrounding all of those atoms. A substitutional alloy happens when the atoms of the metals have similar radii, and it actually shifts the structure around to make room for those similarly sized atoms. So substitutional alloys versus interstitial alloys can change the properties a little bit. We're not going to dive super deep into that. You just need to know that these two different types of alloys exist and which one is which. And I think that's where we're going to stop today. Oh, there's the bell. That was good timing. We will be doing some of these practice problems in class, but the answer key will be up on Schoology so that you can check your work as you go along. Thanks, and I'll talk to you later. Bye.